Hello and welcome to this virtual lesson for National 5 Chemistry. So if you've seen the plan for this week, you'll notice that I've made a slight change of plan. So I had said that we would look at metals, but I actually decided it would be better to finish off the nuclear chemistry topic. So last week we covered types of radiation and nuclear equations, and I said we were going to cover half-life and uses of radioisotopes at a later stage. So rather than postponing that, I decided it would be better just to get that topic concluded. So we're going to cover that this week. So we'll begin with some starter questions. So pause the video just now and try and answer this question, please. Okay, moving on then to the answers. So part A said state where the radioactive decay occurs in an atom, so that's just the nucleus, that's just knowing that radioactive decay is to do with the nucleus. And then part B, phosphorus-32 decays by emitting radiation. During this decay, the atomic number increases by 1. Name the type of radiation emitted, and that is beta radiation. Okay, so question 2. Pause the video now and answer this question. Okay, and moving on to the answer. The correct answer for that one is D. So Y goes straight through between the negative and positive plate, meaning Y must have no charge, so Y must be gamma, so that gets you down to C and D, and X is attracted to the negative plate, so remember opposites attract in chemistry, so X must be alpha because alpha is positively charged, so the positive gets attracted to the negative plate. Okay, so as usual, we've got some background information in this presentation and some key knowledge that you do need to write down. So we're going to be learning about half-life and uses of radiation, like I mentioned. So first of all, we're going to look at how radiation is measured and talk about what the half-life of a radioisotope is. You should know that the half-life of a radioisotope is constant, and we're going to look at how we can use radioactive isotopes to date materials, carrying out calculations using half-life, and giving some examples of the uses of radiation. So first of all, let's look at measuring radioactivity. A Geiger counter, or also known as a Geiger detector, so it's named after the scientists who developed it. This can be used to find out how radioactive something is. So it measures the counts per second, so you can see the reading on this one. This is probably a slightly old-fashioned looking one, but you can see it measures counts per second, and that gives an indication of the number of nuclei which are decaying every second. So every time there's a particle of ionizing radiation emitted, if it's detected by this detector, that corresponds to one nucleus decaying. And the higher the reading, the higher the activity of the material. So you might not have seen the Geiger counter before, but you might recognise the sound they make, so I'm just going to play that for you. So Geiger counters make that really distinctive sound. I'm not going to go into the details of how they work and why they make that sound, but I will post this YouTube link in the description for this video and on the assignment if you want to find out more about Geiger counters and how they work. But the key thing to know is that radiation can be measured as counts per second, and the higher the counts per second, the higher the activity of the material. So if a radioactive material has high activity, that means it's very radioactive and there's a lot of nuclei decaying every second. Okay, so half-life. The half-life can be given the symbol T half. And the half-life of a radioactive sample is the time taken for half of the atoms in the radioactive sample to decay. So in the time of one half-life, the activity of a sample will fall to half of its original value. And the original value is just the value at the start of whatever period of time you're measuring, because the total activity always falls by half in the time of one half-life, no matter what the original value was. It's always going to half. And the total mass of the radioisotope present will also halve in this time. So these are some key things to remember about half-life. So in the time taken for one half-life, half of the atoms in the sample will decay. That means the activity of the sample will halve, and the total mass of the radioisotope present will also halve. So Each radioactive isotope has a particular half-life, and that can vary from a fraction of a second to millions of years. So just a couple of examples. Carbon-14 has a half-life of 5,730 years. You might have heard of carbon dating, and this is the isotope that's used for carbon dating. And yttrium-90 has a half-life of 64.1 hours, but like I say, it varies from a fraction of a second right up to millions of years. The half-life of a radioisotope is always the same. It's not affected by temperature, pressure, physical state, catalysts, or chemical reactions. So the reason half-life isn't affected by any of these conditions is to do with the fact that radioactive decay, like we said in the starter question, occurs in the nucleus. So the nucleus of the atom doesn't take part in any chemical reactions, because it's surrounded by this shell of these shells of electrons, and it's only the electrons that are affected by chemical reactions. Similarly, the nucleus is completely independent of temperature, pressure, physical state. So the reason another reason why the half-life is always the same, and the reason why it can be so different for different nuclei, is it's really down to sort of quantum physics. So you'd have to look into this in a lot of detail to really understand, but the chance of any particular nucleus of any particular atom decaying depends on, there's a probability associated with it, and the probability depends on the structure of the particular nucleus and the number of protons and neutrons, etc. So that's why the half-life of a radioisotope is always the same. It's just to do with probability of any one nucleus decaying. And the probability associated with one nucleus decaying leads to a consistent amount of time for half of the nuclei in a sample to decay. I find the concept of half-life really interesting. It's quite hard for me to explain it in much detail on here, but it's something that you might be interested in looking up, and I'll maybe try and put a link for that as well. So make sure you've got the information down on this slide, because this is key knowledge that you need to know. So the half-life can be determined from a graph, and you need to know how to do this. It's fairly nice and simple, as long as you can remember that the half-life is to do with the activity or the mass of a sample halving. So if we have to determine the half-life from a graph like this, we have to look at the value at the start. So the starting value is 80 counts per minute, and then we just need to work out what half of that value is. So half of 80 is 40, and then we're just going to look at the time taken for the activity to fall from 80 to 40. So 80 is times 0 on this graph. If we go down to 40 and we go down to where this line, which is showing the activity, the point at which that reaches an activity of 40, and then if we just look down to the time at which that occurs, we can work out that the half-life of this sample is 5 days. So I would like you to attempt to sketch this graph. I will post the PowerPoint on Teams, so you might want to go into the PowerPoint and copy and paste it and print the graph out if you've got a printer available to you. But I would like you to attempt to sketch the graph and draw your arrows in, just to remind you how you would work out the half-life from a graph if you need to. So make sure you pause the video now and take this information down. So we're now going to look at a couple of questions. You don't have to copy these questions down. Hopefully you can see the video or the PowerPoint well enough to answer these videos just by looking at the slides. So this question, try and determine the half-life of technetium-99 from this graph. Okay, I'm going to run through the answers then. So the starting value is 1, so we're starting with a mass this time, but remember the mass and the activity, both of these things will half in the time of one half-life. So half of 1 is 0.5, and we're then just going to look at the time taken to fall to 0.5 from the start. So that gives us a half-life of 6 hours. Okay, example 2. This one, I know the scale is a little bit trickier to read, see if you can determine the half-life of iodine-131 from this graph here. Pause the video if you need to. Okay, so I'm going to run through the answer again. Hopefully you figured out that the half-life is 8 days. My slide's not in order this time, but we started at 100 and half of that value is 50, so we're just going along to find out how many days it took for the mass to fall from 100 to 50. The units are a little bit unusual here. PG, I think that stands for picograms, which is a very, very small number of grams. So we're just looking at the time, so that's 8 days. Okay, so hopefully you feel reasonably comfortable with working out half-life from a graph. So as well as working out half-life from a graph, you may also be asked to work out the fraction, percentage or mass of a radioisotope remaining after a given time, or to work out the half-life as well if you're given suitable information. So those of you who have studied physics, you may complete these questions using a different method to the one I'm going to use if you prefer. You might even have a different way to work out half-life from the graph, although I expect you would do that in the same way. So we're going to call these half-life calculations. I'm going to go through 3 examples and then I'm going to give you some examples to complete yourselves. So these are the 3 examples that we're going to work through. I would really recommend that you write down the question as well as writing down the answer. I'm going to switch over to a pen and paper to go through these, so if you want to, you can pause the video now and write down example 1 and then come back and write down example 2 once we've gone through it, or you can just pause the next part of the video where I'm writing it down, because I do have the questions in the next part of the video as well. I hope that makes sense. So we're now going to look at 3 examples of half-life calculations. Example 1 says, what fraction of the activity of a radioactive sample will remain after 3 minutes if the half-life is 30 seconds? Okay, so the first thing that we need to do is make sure that both of our numbers are in the same units. Now, at National 5 Chemistry, I'd expect you to be able to convert minutes into seconds, so that's 180 seconds. So we're looking for what fraction of the activity will remain after 180 seconds if the half-life is 30 seconds. So this question is asking for a fraction. And what we're going to assume, we're going to write this out just thinking about each half-life in turn. So we're going to imagine, you can even call it time equals 0. At the start, we have a hole. And then after each half-life, the fraction of the activity of the sample is going to decrease by half. So we're going to go from 1 to a half to a quarter, etc. And each time we halve the fraction of the activity, or this could be the mass, each time the amount of the radioisotope halves, that's going to be 1 half-life. So I like to do it as writing my fraction along the top and then writing my time underneath. So that's going to be 30 seconds, so that's 1 half-life. 60 seconds, that's going to be 2 half-lives. So we're going to go to 1/8. Now you can just keep going until you figure out the answer. So 1/8 is going to be 90 seconds. So each time we're just adding on 30 because that's the half-life. Okay, and then we're going to go to 1/16, 120 seconds. And then your math is going to have to start getting quite good. We're just, each time the fraction is halving, which means the number on the bottom of the fraction is timesing by 2. So 1/16 becomes 1/32, and that's 150 seconds. So again, we're just adding 30 seconds each time. And then 1/32 becomes 1/64. And then that is when we finally get to our 180 seconds. So after 30 seconds it's half, 60 quarter, etc, etc. And then after 180 seconds we get to 1/64 of the original activity. Okay, so when I'm laying out my working like this, each of these curly arrows going from one fraction to the next, that represents one half-life. So in 180 seconds, we've gone through 6 half-lives, and that leads us to 1/64th of the original amount. Okay. So we're going to look at example 2 now. So example 2 says, after 32 days, the activity of a sample of uranium-231 is found to be only 6.25% of the original activity. What is the half-life of uranium-231? So this time we aren't given the half-life, but we're going to go through exactly the same process in terms of our working. This is given in percentages instead of fractions this time. So instead of starting with 1 and then going to a half, a quarter, an eighth, etc., we're going to start with 100%. And we're going to just think about each half-life, that percentage of the activity is halving. So we're going to go from 100 to 50 to 25. Just halving that each time. And then you can use a calculator for this if you want to. So we get to 6.25%. So each time, just like in example 1, I was looking for a time of 180 seconds, and I'm just continuing with this process of working out the fraction after each half-life until I get to the value that I want in the question. So in this question, it was 180 seconds, so that's why I stopped at 1/64th. This time, we don't know how long. Oh no, we do know how long it is. We know that this whole time is 32 days, and we know that we're looking for 6.25% of the original activity. So we don't know how long each half-life is, but we can work out how many half-lives there are altogether just by drawing our little curly arrow from one fraction to the next. So each curly arrow represents one half-life. So that's half-life 1, half-life 2, half-life 3, half-life 4. So what we find is we've got 4 half-lives to get from 100% down to 6.25%. And those 4 half-lives have taken 32 days. So 4 half-lives in 32 days means that each half-life must be 8 days long, because 32 divided by 4 is 8. And if you want to, you can just put that number back in. So if this was 8 days, then we'd have another 8, so we'd get to 16. Then we'd have another 8, so we'd get to 24. And then, just like we thought, after 32 days, we would get our 6.25% if the half-life is 8 days. So that's just a way of going back and double checking your answer. So we're going to look at another example now. Again, it's going to be slightly different, but we're going to work it out in the same way as the previous examples. So this example says the half-life of cesium-137 is 30 years. What mass of cesium-137 would be left after 90 years? So the half-life is 30 years, and we're asked for what mass is left after 90 years if 100 grams was there at the start. So this is slightly different again, because instead of being asked for a fraction or a percentage of the original, we're being told a mass. But remember, just like the activity of a sample halves every half-life, the mass present in that sample will half every half-life, because every half-life, half of the nuclei decay and are no longer the same thing. So the total mass of whatever was there will half each half-life. Okay, I've said half quite a lot in this video. So we're going to start with 100 grams. 100 grams was there at the start, so we're going to go from 100 grams down to 50 grams, down to 25 grams, and you could keep going, but let's keep track of the time. So each half-life is 30 years, so 30 years, after 30 years, our 100 grams is going to go down to 50. After another 30 years, it's going to go down to 25, so we're adding on 30 each time, so that would be after 60 years, it would go down to 25. And then we're going to go from 25, we're going to half again in another 60 years, another 30 years. That would give us 90 years. So we're going to each period of 30 years halves the total mass. 25 divided by 2 gives us 12.5 grams. So after 90 years, 12.5 grams would be left. Okay, so here are the answers to question 1 to 3. Question 1a, the half-life is the time taken for half the atoms in a radioactive sample to decay. Question 1b, the total mass left after 60 hours is going to be 12.5 grams. Okay, because we just take the starting mass, half it each time we half it, that's one half-life, so we're adding on 15 hours each time, and so after 60 hours our mass left is 12.5 grams. Question 2, the half-life is 2 minutes, so we were told it goes down to an eighth of the original in 6 minutes, so an eighth, if we start with 1, it takes 3 half-lives to get to an eighth, and if 3 half-lives are 6 minutes, I should really write minutes in here, then 1 half-life is 2 minutes. Question 3, we were asked how long does it take for the sample to reach a reading of 15 counts per minute from 120 if the half-life is 60 hours. So a count of 120 is going to half to 60, and then to 30, and then to 15, which is the count that we're asked about. And each of those stages is going to take 60 hours. So we've got 60 to 120, then another 60 gives us 180 hours altogether. Question 4, I would say, was quite tricky. So I'm just going to show you how I would do question 4. If you have done it yourself, the answer is 0.48 grams. So well done if you got that. So how I got that, so it says in the question that thorium has a half-life of 19 days, and it says 0.42 grams has decayed after 57 days. And you have to calculate the initial mass of thorium-227. So what I would be thinking is, if 0.42 grams has decayed, I'd be wanting to think, well, what fraction of the original is remaining? So if I start with a whole, then I'm going to have a half to a quarter to an eighth. So let's see, I need to work out how much of the original I'd have left after 57 days. So that's 19 days to a half, 38 days to a quarter, 57 days to an eighth. So after 57 days, one eighth remains, because that's what we're calculating here with our half-life. That means that 7/8 have decayed. Now the question tells us that a 0.42 grams has decayed. So if 7/8 have decayed and 0.42 grams have decayed, then 7/8 of the original, so we're going to call the original X, must be the same as 0.42 grams. Okay, so now that you've got a little equation here, then you just divide both sides by 7/8, so X is going to be 0.42 divided by 7/8. Make sure you put the brackets when you do this sum in your calculator, and that gives us, so you can see the way I've laid it out here, so 0.42 divided by 7/8, and that gives us 0.48 grams. So that one I would say is definitely trickier than something that you would get in the exam, but well done if you got it. Okay, I hope you got on okay with the questions on half-life. We're now going to look at uses of radioisotopes, but it would make the video far too long and probably quite boring for me to just talk through lots of different uses of radioisotopes. So I would like you to please go to these links. I'm going to post these in the description for the video and in the assignment on Teams. And have a look at this information on BBC Bite Size about different uses of radioisotopes. So the top one I think is actually GCSE physics, but it gives you quite a lot of different uses. It doesn't talk very much about dating though, especially carbon dating, which is really interesting. This bite-sized link talks a little bit more about how we can use carbon dating to date different objects. So please pause this video, make sure that you've had a read of the information on these pages, including looking at the questions and the videos if there are any videos on the pages, before taking a note of the examples on the next slide. So the main thing when you're looking at these videos is, these pages, is just to think about why different isotopes are suitable to different applications, considering the type of radiation, how damaging it is, how far it can travel, and also the half-life. And that's what we're going to focus on in the next page. So I know this seems like probably quite a lot of information, but I would like you to take this in, just because it is important for you. You don't necessarily need to learn lots of these examples, but you do need to understand why the different types of radiation are used for different applications and why different half-lives are used in different applications. So the first example is using isotopes as tracers in medical scans. You know what, I'm not going to read out this whole table. I think you can read this for yourselves and write it out for yourselves. So I hope it all makes sense, and we will have time to do a little bit of revision of this topic in class, and we can talk about any questions then. So make sure you've taken down this information, and then here is a little summary of what we should know at the end of this video lesson. So we should be able to explain what the half-life of a radioisotope is. We should know that it's constant. You should be able to explain how radioactive isotopes can be used to date materials. If you're at all unsure on that, you need to go to the BBC National 5 Chemistry link, because it talks about carbon dating in particular and how it can be used to date materials. And we should be able to carry out calculations using half-life and give some examples. You don't have to memorise them, but I think it's useful if you know maybe 2 examples of the uses of radiation. So as always, I've tried to keep the video lesson nice and short, or at least as short as possible. And if you think you need extra practice on this topic, then go to the Scholar pages or BBC Bite Size just to check your understanding. Thank you for listening.